Now I have here a system that's sort of close to the system that's described in the first problem, except of course that the bar itself, or the track, or whatever you want to call this thing, has itself a moment of inertia, but we're really interested in, and has therefore kinetic energy when I wave it back and forth, but we're really concerned with the kinetic energy of these two magnets. Now here are the two magnets, and as I wiggle this back and forth, they have a kinetic energy, and of course I can also feel the resistance to my attempt to wiggle the thing back and forth, and that's due to the moment of inertia. In any case, these things have some kinetic energy. Now I'm going to move them slightly so that one is on top of the other. Okay, and they are, let's assume, the center of these things is at the same distance from my axis of rotation, where I'm holding it, as the center of the two magnets was. In other words, the two magnets would be like from here to here when they were separate, and now they're together, one on top of the other, and they're centered here. They're still centered at the same point, they just don't extend as far. And I have some kinetic energy now when I wiggle it back and forth. Now, do I feel a difference between this and this? Well, no, I'm not going to feel that difference. It's going to be pretty small. But the question is there a difference? So we get to the question by asking, is there a difference in the kinetic energy of the two magnets if they are centered 10 centimeters from the axis of rotation, as opposed to one being centered at 9 centimeters, the other at 11 centimeters? Now, the middle is still at 10 centimeters, but they're spread out more. Part of the magnet is, there's some mass closer to the axis, and there's some mass further from the axis than what we have here. You would think that everything would average out, but remember that the kinetic energy, well, let's see how the kinetic energy behaves. Let's see what it's proportional to. Okay, so what I want to do is, let's assume that we have 50-gram mass, and they're either one at 9 centimeters and one at 11 centimeters, or two of them at 10 centimeters. That's the stated problem from the axis of rotation. Now, kinetic energy is 1/2 mv squared. Alternatively, kinetic energy is 1/2 I omega squared, as everybody was supposed to know today, having done the homework and the documents that were assigned. Most people didn't do those, and most people didn't seem to be aware of this, but it's kind of natural to be thinking in terms of this and maybe not have this occur to you, even if you knew it. Okay, so I only saw one or two people that quoted this result, but that's the one that we'll ultimately be wanting to use. However, this one works just fine. Now, we know the mass, and let's do, okay, well, if we know the mass and the velocity, we can find the kinetic energy. Let's take one of the masses at the 10 centimeter position. Now, we know its kinetic energy is going to be 1/2 its mass, which is 50 grams, and people wanted to use 0.05 kilograms, and I can go along with that very easily. 0.05 kilogram mass multiplied by the square of its velocity. Now, what I saw several people doing is using 5 radians per second as the velocity. 5 radians per second is not a velocity, it's an angular velocity. This is not an angular velocity, it's a velocity. It's how fast the thing is moving. Now, at this point, before we went on with the problem, we all went outside. It was kind of chilly, but I was dressed as lightly as anybody. And people, you know, I asked people if anybody objected to going outside. Not that cold, it was nice and sunny, but temperature's still probably 40 degrees. Everybody said, okay, we'll do it, and tried not to keep people out there too long. I asked everybody to go out in the open area in the middle of campus and get at least 15 feet away from anybody else. And people did pretty well with that. Some people stayed a little too close, but a couple of words, and people separated themselves a little more, and it was fine. Then I asked everybody to, and I demonstrated, take 3 steps forward. Now, I can't take 3 steps forward on campus. I'll take little steps. 1, 2, 3. So everybody went 3 steps forward. Then I said, okay, now turn and point back to the center. Turn and point back to your original position. Now I'm going to do this this way. So here I am turned and pointing at my original position. Then I ask everybody to keep their finger pointed at that point and take that as the center of the circle. And then take 3 equal steps around. Well, first I asked people to go around the arc of the circle. So people went around the arc of the circle, and that arm kept pointing at the center. Now, we probably looked like a bunch of escapees from a mental institution, and no stigma there, because some people do have legitimate and not self-induced reasons to be in there, and that needs to be handled respectfully. But you know the image I'm talking about. Maybe I shouldn't mention it, but I did. You know, we didn't look like something we would want to go out in a big public place and do a lot of. Okay, we looked a little aimless, and you know, it was a little humorous, but okay. So then I say, well, go out to the same point, and now take 3 steps along the arc of that circle you just walked. So people took their 3 steps, and I pointed out that if their arm stayed pointed at the center, the arm would have rotated through 1 radian, because 1 radian is the distance of the angle you go through, the angle corresponding to a distance along the arc of the circle equal to 1 radius, equal to the radius. And then I asked, you know, questions about, well, how many radians did you go through in going around the whole circle? We wanted to reinforce this idea, and we did that just before we came back in. So we came back in and continued with the problem. So kinetic energy is this. We want to find the velocity. Okay, well, the velocity turns out, we know we're doing 5 radians per second. Let's look at it this way. In each radian, we go a distance equal to the radius. So if we multiply 5 radians per second by our radius, we get 50 centimeters per second. 50 centimeters corresponding to the distance we would go along a circle of radius 10 centimeters as we go through an angle of 5 radians. Okay, so we determined that the velocity is 50 centimeters per second. Now this has been introduced, it's been reinforced, we've done it in class, it's been assigned on the worksheets. So this is a fact that you really need to know, and I think you need to know this as a fact. I think you're better off knowing this as a fact than as a formula to be memorized. Although, if you want to memorize a formula to back yourself up, okay, check it out, though, when you use it with your understanding, because it's real easy to get those formulas messed up. Okay, so half a meter per second, 50 centimeters per second. So what's our kinetic energy? Well, everybody can do that. Everybody's been able to do that for a long time. Just 1/2 the mass times the square of the velocity, and we get 0.00625 joules. I say everybody knows that formula and how to use it. Not everybody at this stage still, unfortunately, knows how to do the units of this calculation. You really need to review that, review previous notes. Make sure you understand units. Okay. So, with that caveat, right there is your kinetic energy. Now, at 9 centimeters, well, you can go through the same process with a 9 centimeter radius. The only difference is you're going to multiply your 5 radians per second by 9 centimeters, getting a speed of 45 centimeters per second, or 0.45 meters per second. I think I lucked out and calculated this correctly. Now, I calculated it by proportionality. You got 9/10 of the radius, so you've got 9/10 of the velocity, and the kinetic energy goes as a squared velocity, and the square of 9/10 is 81/100 81%, and I did 81% of this. 80% was easy. The 1%, all I had to do is get stuff in the right place, and I think I managed it, but you can double check me on that. And then I did similarly with the 11 centimeters. 11 squared is 121. That gives you 21% greater than this. So 20% is 0.0125, and then you try to get the 1% in the right place, and I think maybe I did it. Okay, so these are the two kinetic energies. So the kinetic energy of two 50-gram masses at 10 centimeters is 2 times the kinetic energy of the one, or 0.0125 joules. The kinetic energy of 50-gram masses at 9 and 11 centimeters, well, you're going to add the kinetic energy of the mass when it's at 9 centimeters to the kinetic energy of the mass that you placed at 11 centimeters, and you get this. And I think it's 0.1265. Now, again, check me. I'm still not 100% sure I got everything in the right place, and I'm not particularly interested in whether I did or not, although I prefer that I'd done it correctly. I want you to check me on this. Okay, I want you to run through the calculation, and if you get something different, well, you beat me on that one, and that's fair. And you can feel happy about that. Now, this exceeds this. You have more kinetic energy here than you had here. The difference being, and you can take the difference, I think you got 4 zeros and a 125. Okay. And I'm just looking for something where I can check that. Yeah, be 4 zeros and then a 125. And actually, I think maybe I said it's a 125, and I think I got a number in there that isn't right. And again, check me on this. I think instead of 125, it's 15. Now, having corrected this and then thought about it, I think it's 125, and I think this is 1625 instead of 165. Okay, so I did have a mistake. I've written this down right. At least my present opinion is that I had the mistake here. It should have been 12625. Since 625 and 625 is a 125, okay, and again, I'm back to where I was because I don't think that's right, and now I think it's right. Okay, 625 times 2 is 125, and 1250. If you do 625 and 625, you get 1250, and that's going to add it's going to add a 125 starting at this decimal point, the fourth figure, the fifth figure, 1, 2, 3, 4, 5 figures, okay? And that's where we start the addition. The 125 actually starts at the fourth figure. Hope you're enjoying my internal debate here. The way I originally calculated this was correct. I just wrote it down wrong here. A 50 and a 75 is 125. And then we have a 625 out here in the next decimal place. 2 625s add to a 1250, and the 1 is going to go in this decimal place, taking the 125 up to 126, and then we still have the 250, which gives us the 25. This was right all along until I corrected it and then fixed it. And this is now right. I left the 2 out here. Okay. Anyhow, the bottom line is then that this is about 0.1%, 1 part in 1,000, more than, where is it? More than this. Okay? This is a little more than this, 12625, and this is 125. And I say it's 0.1% more, and now I think it's 1% more. Okay, now I'm saying that it's 1% more, because you're going from basically 125 10,000ths to 126 10,000ths. But it's actually 126.25 10,000ths, very close to a 1% difference. Now I could easily edit out my internal debate, but it's worth keeping in there. Just so you get the process of mental arithmetic and checking. and naturally, you should still check my calculations.